Well, depends on which side of the x-axis you're on. You guys see it? What did I just highlight? Tell me about those orange highlights.
They're all the same. Each row is the same.
They're not this. They're this. There's the word. Yes, horizontal. Thank you so much. Was that just like so obvious that you felt insulted that I was asking you? No? Yes? Possibly? Okay, fair enough.
Slightly.
So here is the pattern. Here's the pattern. Whenever your differential equation, dy dx, depends only on y, you should have only horizontal, like in a horizontal pattern, all of the little tick marks should have the same slope, right? Okay. Now, as far as a solution curve goes, a solution curve through the point 0, 1, we're kind of left to assume that that's 0, 1 right there. So, some ideas about a solution curve. I started you off pretty easy here. A solution curve should mimic the slope field, and really technically it should only go through the initial condition. We can't say for sure whether it goes through other points, at least based on this one. So you want to carefully navigate your way through and, oh, what did I do? I did 1, 1. What am I doing? Let's go with 0, 1. There's 0, 1. You all were going to just let me sit there at 1, 1, weren't you? Okay, there we go. 0, 1. I notice I avoided the other points, not because they're for sure not on it. I just don't know for certain that they are, so I'm going to leave those off at this point. Can anybody explain how could I have drawn my solution curve down there? What would I have needed? What would tell me my solution curve is down there? Yeah, if I had a different initial condition. So if instead of this, it said 0, negative 1, that would put my solution curve down below, right? So wherever you draw it is simply going to be fully dependent on wherever that initial condition point was given. And then I'm getting a little bit ahead of myself here, but I thought I could show you this. We have talked about this. We talked about this, of course, over and over and over last year. If I were to take this differential equation and actually try to solve it, you all said, hey, it looks exponential. Let's get a little bit of practice again with this, and we'll do a lot more with this in 6.3. If I was going to actually try to solve this formally, it was the AP test or whatever, or one of our tests, what would I have to do first? Separate the variables, that's right. So get something like dy over y is equal to 2 dx. I typically am going to try to keep everything as much as I can over there with the x's. You could bring the 2 over with the y if you wanted to, but I feel like it's easier because I am eventually going to try to solve for y to just leave stuff away from the y if possible. Once you've done that, what would come next? Do you remember? We've separated the variables. Yeah, we're going to find antiderivative. So antiderivative of both sides. The right side is going to be 2x plus c. How about the left side? ln. And remember that this is where it gets really important that you include absolute value of y. ln of absolute value of y equals 2x plus c. Can anybody explain, I know we talked about this in my classes last year. Can anybody explain why we put the plus c over there with the x's but not one over here with the y's?
Because after you add it together, it's a new constant.
It would just be a different constant, right? If you subtracted one c from the other c. Yeah, you're right. Okay, fair enough. This is where I typically will try to use my initial condition right here. You can do it later if you want. I tend to do it right here. And this is typically worth something, right? Having the plus c in there and applying the initial condition. So we're going to say that y is 1 when x is 0. You guys remember what ln of 1 is? And 2 times 0 is 0. Okay, so that just means c is 0. And this is where we want to remember something that'll potentially help us a little bit later. We want to remember if the absolute values mattered with the initial condition. Do you remember this?
Yeah.
Like when I plugged in that 1 for y, did the absolute values have to change the sign of the input for this to work? It didn't. We'll talk a little bit about that later on about why that's important. But the bottom line is we would go, knowing what c is, we would say natural log of absolute value of y is equal to 2x. And the final goal would be to solve for y. So I'm going to go e to both sides. So that's going to give me absolute value of y equals e to the 2x. And this is where remembering whether those absolute values make a difference or not, as far as the sign, the plus or minus, is going to come into play. A lot of times people just say, oh, just drop them. Well, we actually here can like sort of drop them, quote unquote, but we are actually just evaluating it. So remember that the 1 was a positive, right? That means all of your y's here, we can see from our sketch earlier, all the y's will be positive. So when you evaluate a positive number with absolute values, does the absolute value really do anything to the positive number? No, the absolute value of a positive is still just a positive. And so that's why it kind of appears that we're just dropping the absolute values, but in reality, we're evaluating that expression. And based on what we did before, we know that it's really absolute value of a positive. You'd get something like that. Then you all said, hey, it looks exponential, and it's exponential. So obviously that was a good read on your part. And we're not going to do that with all these. I just thought I would make that connection from our old skills and old material from last year. Caroline.
So if it was 0 and -1 as the initial,
Mm-hmm.
would it be like y equals negative?
Yeah, so let's do that really quick. So let's say that was the case. Let's say instead of that initial condition, we had 0, -1. That, of course, would have put our solution curve down there. And so let's go through this really quick. If we, like on this step right here, if this were the case, we would get ln of absolute value of -1 equals 2 times 0 plus c. And we'd say absolute value of -1 is 1, and ln of that is 0. So you'd still get c equals 0, right? But then, as you went through like this step here, you e both sides, and then you get to this step. This would be the step where you would say, oh, that's right. When I applied my initial condition before, the absolute values made a difference, right? They essentially turned the negative into a positive, and so they had an effect. And so we had to do the opposite of the input. And so what we would say then is that the absolute value of y is -y, and then in solving for it, we'd get y equals -e to the 2x. That makes sense? And that, of course, matches our solution curve. Thanks for asking. Yeah. Anybody else? All right, beautiful. Okay, so let's take a look, if you haven't already done so, at our next slope field. Take a look at number 3. dy dx equals x minus y. See if we can draw that. And I think, again, we should be able to start to see a pattern take shape. So fill out the whole thing, and we'll do a solution curve through -1, -1. And we are not going to solve this one yet. This will be one that by the end of this chapter we'll be able to solve. This is actually going to be, I think for the first semester, this is going to be our final like bonus topic, first order linear differential equations. If you try to do this one using our, the skills we already have, you're going to get stopped pretty quick, but we can just learn a new skill, and that's what we'll do by the end. So anyways, to give this one a shot. So you guys can definitely make a table here. One thing that I'm a fan of is trying to notice patterns within it. You guys pick up on the idea that wherever the x and the y coordinates match, because you're subtracting them, you'll get a dy dx of 0. So all throughout here, you should be getting 0 slopes. And so you can start to kind of replicate this in terms of a pattern. Once you see that pattern, a table is a great place to start to kind of see the pattern. But once you do, feel free to use that. It's okay. I'm not going to go through and pour over your arithmetic and say, oh, you didn't figure it out for -2, 3 or something. It's okay.
Really? They had rashes. It's so annoying.
She'd be like, back pain, back pain.
It's
I'd be
okay.
like, that's a rash. She'd be like, no, back pain. And I'm like, no.
It's okay. The first day we got there, our translator did.
So then wherever x is 1 bigger than 0, you should get a slope of 1. What do you guys think is going on? What is the deal with this? Let me try and fix this.
That's true.
What do you guys think is going on right there on the graph of y? Slant asymptote. Yeah,
Wow.
good. Alyssa is with it. She's on. She's on it. Yeah, absolutely.
Never on it.
Okay, so let's fill some stuff out here. Did you guys get basically kind of an X pattern, at least through part of it? I mean, there's more to fill out, but did you guys get that?
Yes.
Okay. And then let's see here. Out there at 2, 1, the slope would be 2. Down here would be looking at -2. And then kind of the same routine here and here.
Symmetry.
There's a lot of symmetry here. You can use that to help you. And then what about the, how about the first, second, third, and fourth quadrant empty dots right now? What would be the slopes there?
1/2.
Either plus or minus 1/2, right? Yeah. So, I don't know, let's go with that, and that, and that. And then wherever x is 0, save 1 point, the dy dx will be 0, right? So I'd say all along the y-axis, we should be getting 0 slopes, not at the origin, but then everywhere else on the y-axis, we'd get a slope of 0. So I'd say something like that. Does that make sense? Okay. Why did I leave the x-axis totally blank? Slope is undefined whenever y is 0. Yep, that's exactly right. So in those cases, just leave those points, whatever they are. In this case, it's the x-axis. Just leave them blank. Okay. Yeah, so I totally picked a weird, I don't know, maybe I just didn't vet this out, or I don't know what it is. I picked kind of an odd point, but this will be kind of a cool illustration, I think, with 1, 1 being our initial condition. So if 1, 1 is the initial condition, that point, of course, is here. Oops. Come on. I've been having issues with my little styluses or styli. Hey, there we go. There's 1, 1. So isn't 1, 1 on the part of the graph that's on one little branch of that x? Right? So, I mean, if you were to say, well, golly, what does that look like? You would have to kind of do that, like try to draw a straight line, wouldn't you? And say, well, that kind of looks like my solution curve. And, you know, Blake and Darian were like trying to figure out what the solution curve would look like. And they got something that kind of agreed with that. Essentially, y equals plus or minus x.
Yeah, or the square root of x squared.
Right? Yeah, square root of x squared, which ends up being plus or minus x. And so these two guys had this, something like that, which does look an awful lot like an absolute value, doesn't it? Mm-hmm. Yeah. So, I don't know. Do you guys know what you would call this solution curve? Like in general, like if I didn't pick 1, 1, this actually, you can see the curvy nature to this a little bit, can't you? So for instance, let's do this. What if I had picked a different initial condition? What if I had said, instead of 1, 1, what if I had picked 2, 1? What do you think the solution curve would look like there? It is a hyperbola, that's right. So it would actually look like this. It would kind of come in and do that. But then as soon as we got to the x-axis, we'd have to go with an open circle. What I want to bring up here is with a solution to a differential equation, it has to have a couple of characteristics. So A, it has to be a function. It has to be a function on the part of the graph that contains the initial condition. So if I were to continue on down this way and do something like that, it's a little lopsided, but you get the idea. Wouldn't that cease to be a function? Right? It wouldn't be a function anymore. So I'd have to pick one side or the other. And that's why I was kind of getting at the plus or minus, not really thinking about the 1, 1. It's like, oh, you got plus or minus whatever it is. Well, is it going to be the upper half or the lower half? Why do I pick the upper half instead of the lower half of the plus minus on the hyperbola? Like, why would I pick? Because the initial condition is up there, right? So since the initial condition is right there, I'm going to pick the upper half as opposed to the lower half. Yeah, so the whole 1, 1 thing, as far as the solution curve, aren't we really describing those asymptotes that kind of govern the hyperbola's behavior? That's what that one's actually describing. I didn't really intend to think that one through, but, or maybe I did and just forgot, but that's kind of what we got. So that's kind of a cool result. Okay, so I think at this point, unless you have a question, let's move on. I really do hope that, you know, later on when you get to an AP test that you do get to draw the slope field. I feel like if you just take your time, it's a pretty easy point or two. So you'll get lots of chances to practice that. There are a few extras in your packet as well as on your web assignment. So let's do a couple of matching exercises here, and we want to start talking about patterns. So let me get this to fit a little bit better. There we go. So if you guys would, take a look at number 7, 8, 9, and 10, and let's try to match these up with A, B, C, D, and we can talk about some efficient ways of doing that. But please notice this. All of your options on 7, 8, 9, and 10, they are all differential equations, and we're supposed to match those with slope fields. Later on, we'll take a look at some of these where you're supposed to match solution curves with slope fields. So you'd approach that perhaps a little bit differently. Take a minute if you haven't already looked at this one. I'm just looking around. Okay, we're working still, but a lot of you guys have already tried this one. This one through. So, I don't know, let's go in order of number 7 through 10. Lenny, what do you think about number 7? What did you match 7 to? Okay, why did you pick C for number 7?
Because the other sign is the only one where it's kind of the slope decreases, increases over time. That C is.
Sure. Yeah, so you obviously see a cyclical pattern, periodic pattern with that. I think there's some other reasons you could list. Anybody see anything else? Like why would, he's right, of course, 7 is C. And he said, I saw the cyclical pattern. Do you see anything else that might indicate 7 goes with C?
Sine of 0 is 1.
Yeah. You actually could kind of plot some points, essentially, plot some slope field points and match those up. I think that's a good way. In fact, of course, McKenna, with more complicated ones, that's kind of what you have to do, right? Okay, number 8, Cameron, what do you think goes with number 8? This is kind of cheating a little bit, right? Because didn't we just do this one? So, Cameron, aside from the fact that we already did one just like this, what are some other indicators that D is the only one that could go with 8?
Well, you could just kind of plug in, like last time we plugged in 0, 0, or 1, 1.
Yeah. Kind of like what McKenna suggested. Right, yeah, you could plot some points and you should be able to see that pattern taking shape. Okay, we'll come back around to that one at the end, but Cameron definitely is right. Sean, how about number 9? Which one did you pick to go with number 9? A, okay. Why did you pick A for number 9? Horizontal pattern, yeah, there we go. So of all the differential equations we had there, only one of them depended only on Y, and only one of your slope field options has a horizontal pattern to it. So yeah, that's good reasoning, makes a lot of sense. Of course, by process of elimination, that leaves 10 to go with B. Why does that make sense beyond just the obvious that's the only one left?
Like the diagonals are all the same slope.
In a vertical pattern, right? Yeah, in a vertical pattern for B, if you just draw a vertical line anywhere, right? So if you draw a vertical line here, you see that all the slopes are the same within that vertical pattern, and that is characteristic of dy dx depending only on x. So guys, if we swing all the way back to number 8, dy dx depended on x and y, so you should see neither a vertical nor horizontal pattern there, but some kind of diagonally, sometimes kind of complicated, but there should be some element of a diagonal pattern to that. And you see, of course, that happening in option D.
And for 10, like he solved it like 1/2 x squared plus c.
Yeah,
Parabola.
which matches a parabola-like shape in the slope field. Sure, yeah. I think those things all go together quite well. And then by that same token, with number 9, you could solve. You could solve number 9. You guys recognize what number 9 looked like if we solved the Diffie-Q? You can cheat by looking at the slope field.
Exponential.
It's exponential, yes. Exponential, and you can see that sort of an exponential pattern right there. Okay. Any follow-up questions? I've always thought slope fields were kind of fun. Little tedious, but fun nonetheless. Okay, so final example here for us in this section is right here. And this, of course, is same concept, but approaching it from the opposite side. We've got one slope field. We're given 5 options that potentially go with that slope field. But this time, all of the options are given to you as solution curves as opposed to given to you as differential equations. So we can't necessarily use all the exact same strategies. You know, like McKenna Cameron said, hey, let's plot some points and see if the slopes agree with our pattern. We can't really use that here, at least not directly we can't. We can do some stuff to get there if we want, but yeah, so try to match this up. If you have a really good sense of parent functions and what graphs ought to look like, this one actually goes by pretty quick. If you don't, you might have to do a little bit of extra work, but you can still get there as well. So think it over. Got enough time to discuss. Caleb, what'd you come up with for this one?
I think it's E.
Why do you think it's E?
Because it's the only one of those functions where when x increases, dy dx decreases.
Could you say that one more time?
Like, it's the only one where when x increases, dy dx kind of decreases.
Well said. Well said. You guys agree with the E selection? Do you understand his reasoning? It's the only one when x increases that dy dx decreases. Okay. So I'm wondering, did you do a bunch of derivatives to kind of come to that conclusion, or did you just see it?
Like, I kind of just checked the derivatives, like.
Right. So and all these derivatives are relatively easy to find, right? Yeah. So, here dy dx equals 2x. Oops, I'm getting one step ahead of myself. And you could almost kind of check the slopes by doing that. Here, of course, dy dx equals e to the x. And that's the exact opposite pattern, right? But here, dy dx for ln is 1 over x. So this is where we see Caleb's pattern approaching reality here, right? Because as x gets bigger and bigger, isn't 1 over x going to... Now you said as x... Say that again. As x increases...
dy dx decreases.
And let's actually tag something onto the back of that for this to make perfect sense with this. We could say as x increases, dy dx decreases towards 0, right? It's not that it's decreasing towards negatives, because you can see all the slopes on that slope field are positive, right? But as you move further and further to the right, the slope field marks are getting less and less positive slopey and getting closer and closer to 0. And this is one of those characteristics of natural log. If you think about the graph of a natural log, it goes through the point 1, 0, and looks something like that. I think for me, being an old school person where when I was learning this, calculators were brand new, like graphing calculators were brand new, we had to do all this by hand. I would recognize that immediately as an ln pattern, right? And if you guys are well versed in what a parent graph of ln or x squared or e to the x, or whatever it is, looks like, you can see the same thing. But Caleb's idea with the pattern is really excellent. Okay, so that's it for slope fields. Has this been a good refresher? We can do some more if you want. But if it's been a good refresher, we definitely will move on. What do you guys think? Good refresher. Okay, fair enough. So let me give you a preview of what we're going to be doing next. Well, no, I take that back, of what you guys are going to be doing next Monday. Remember, I'm not going to be here Monday, and so I'll be doing a video for this. But there is an intro video for it as well. But let me give you just a brief intro of this.